Hello. So this is for physics 301, and today we shall talk about differential equations. So, so just to write the topics down here. So we want to talk about uh, differential equations in general. In that, we want to talk about initial conditions. What is meant by initial conditions? Uh, in this context, I should also point out that there is a related idea of boundary conditions. It's slightly different from initial conditions, and we'll highlight that later, and that will play a good role uh, later, about 2 weeks later. We should know what is a Wronskian, which we'll cover today. And as an example of this whole topic, we'll discuss harmonic oscillator, maybe damped also. So let's say damped harmonic oscillator. Right. Or maybe we will reach the damped nature of the harmonic oscillator in the next class, but today we might just do harmonic oscillator. This is physics 301 for SIUC. This is just for reference. Date today is 2020, March 23rd, actually. At least that's a recording date. This is late night of March 22nd. Okay, let me clear the board so that I have some space down here and start over with the example of harmonic oscillator. So clear. So we want to discuss what harmonic oscillator is. Let's consider a let's say straight line. I suppose I can draw a straight line like this. So let's, oops. And that's a floor. And I attach a, oops, I don't think I want that. And I attach a spring now. And that's a mass M. And for the time being, let's consider frictionless scenario. So it's frictionless. Later, when we say damped harmonic oscillator, we'll talk about the same system with friction, and that's what will cause the damping. Let's presume this is a stretched situation. So somewhere here is the equilibrium point. So that's x equal to 0. And that's your value x. So you stretch the spring by an amount x, and we know that if it's a simple spring, there will be an elastic force against the stretch, and that's dependent on the stretch x itself, and it's in the opposite direction. So that's that will be shown by a negative sign in our equation. K is the spring constant. So using Newton's law, we can say mass times acceleration is equal to minus k x. Acceleration is second derivative of position, so we have mass times second derivative of position with respect to time. So that's k x. We can rewrite this as divided out by m, and we have second derivative of the position with respect to time is equal to minus k over m. And let me define quantity omega naught square, which is a collection of the ratio of the spring constant over mass m. And omega naught is the characteristic frequency of this system. So we don't have to be talking about k and m. Everything about the system is governed by the ratio k over m. And of course, omega naught itself is related to the time period, right? So there's a periodic system, and there is a time period associated with it. Right? T is the time period. Right? That's the time period. Okay, so that's good. So that's your differential equation, and the goal here is what is to find the position x as a function of time. This is one of the simplest differential equation you can uh, have. And what we ask here is derivative of what function, when taken two times, gives you back the function itself with a scaled quantity omega naught, and it changes sign. And we immediately think of sine and trigonometric functions, sine and cosine. And we typically realize that sine is a solution, cosine is also a solution. And then since there are two different, so this is the second order differential equation, we know that the solution x of t is given as as a cosine of omega naught t plus b times cosine omega naught t. And that's indeed the solution in terms of two unknown integral constants, a and b, which has to be determined with initial conditions. So usually a differential equation is not very much completely specified until you specify the initial conditions. So we have to specify what are the initial conditions, right? So I have to specify what is my initial conditions. So I'll specify it here. So a differential equation always goes with the initial condition. So let me say that at time t equal to 0, specified by x of 0, let it be x naught. And the velocity v at time t equal to 0, let's say that's v naught. Right? And I should specify here that velocity v is dx by dt. Right? That's that defines pretty much all the variables down here. And based on our initial conditions x of 0 and v of 0, we can find a and b. And let's see how do we go about this. Before we'll come back and see how did I really get cosine and sine. Oh, I think there's an error here. There should be sine omega t, right? So let me use an eraser. Oops. So let's B sine omega naught t. How do I find my A and B's in terms of x naught and v naught? So I go back and calculate velocity as a function of time, first of all. So I just take the derivative for that. And I notice this is omega naught A times sine omega naught t plus omega naught B times cosine omega naught t. So there's two equations. And together with the initial conditions, you can see that this first equation implies x naught is equal to, if I set a t equal to 0, the sine function does not survive because sine gives you 1, so x naught is equal to a. And the second equation similarly tells me that v at time t equal to 0 is v naught, and sine function now this time doesn't survive. It is the cosine function that survives, and so it's omega naught times b. And together, once I have a and b, I now have the solution as x of t is equal to a, which is now x naught times cosine of omega naught t, plus b, which is naught over omega naught. So that's using the second equation here, times sine of omega naught t. So this is a very general solution, and based on any initial conditions. And remember, x naught is how much you stretch the spring at time t equal to 0. And while you're leaving, you could give it a kick, and that's your v naught. So that's your complete solution. Let's go back and see how did we arrive at the solution to be cosine and sine. That helps a little. So for this purpose, let me go back and add a new page now. So at this stage, I'm talking about, I want to introduce the idea of a Wronskian. So that's a title here, but again, the equation is the same. The system remains the same. So let me write down my equation. So it's d square x over dt square is equal to minus omega naught square times x, right? And there are various, or let me just see, how would you go about finding the solution? I think the simplest way of saying that the solution is what are the functions that give you back this on the right hand side as a minus omega naught square x, and you will immediately realize that there are many solutions. You can think of x of a to be sine of omega naught t, right? X of t could be cosine of omega naught t. That's surely two solutions. How about exponential of I omega naught t? I is necessary because exponential actually gives you, when you differentiate it with respect to time, it gives back the coefficient in front of t. So I even squared gives you a minus sign, and that takes care of the minus sign on the right hand side. So that's a solution. And actually x of t is equal to e raised to minus I omega naught t. Right? But then I just now wrote four solutions here, and what's actually the solution? Why did I earlier just pick cosine and sine to be a solution? In fact, I can pick any two combinations of this, right? So in principle, x of t could be a cosine omega naught t plus b sine omega naught t. Make sure. And another way of writing the solution could be, someone might be, or sometimes it is nice to nice to write the solution in terms of exponential. So, and let's say it is a prime, just to highlight the fact that this is a different set of solutions. That seems fine. Maybe it's not very surprising, but then one might get curious and ask, is it okay to write a new combination where you have a double prime of cosine of omega t, and then uh, write b double prime of exponential of I omega t. So here I have mixed up this cosine and exponentials, and one might uh, wonder what makes you sure that it's actually a valid combination of solution. And in fact, the point is that you can actually take any two independent solutions and add them together. A linear combination of them is a total solution. But then what do you mean by independent solution? Right? So independent solution, right? Independent versus dependent solutions. So what's the characteristic, or what's the definition of an independent and dependent solution? And that's where the Wronskian comes in. So Wronskian, so let's say there are two solutions. So we're going to, so Wronskian of, so Wronskian is defined in terms of two solutions. So let's say x1 of t and x2 of t, two solutions, is defined as the determinant of, or if you first construct a determinant of the two functions, x1t, this is the first row of the matrix, x2 of t, and the derivative of the x1 of t and the x2 of t. So that's your, that's a definition of the Wronskian. And if the Wronskian is equal to 0, then they're dependent. So then they're dependent solutions. And if this is not equal to 0, then they're independent solutions. And that's the key you want to use to make the right combination. So let's do an example. So let's say example 1 here. So this is example 1. So let's say x1 of t is cosine omega naught t, and x2 of t is sine omega naught t. Good. And what's the Wronskian then? Wronskian is the determinant of cosine omega naught t. The first row consists of the two solutions itself, and the second row involves the derivative of the two solutions. When I take the derivative of cosine, I get a sine with an omega naught in front and with a negative sign, so it's minus omega naught. sine omega naught t. And when I take the differentiation of sine, I get omega naught cosine omega naught t. Right? And I have to take the determinant of this whole quantity. And that gives me omega naught times cosine square omega naught t. And the determinant involves a negative sign, but there is already a negative sign in one of the off-diagonal components, so it is plus omega naught sine square omega naught t. And since we have cosine square uh, plus sine square equal to 1, so that's equal to omega naught, which is not equal to 0, right? So that implies that x1 cosine and sine are are independent, right? Remember, if the Wronskian is not equal to 0, that means it's an independent solution. So they are independent solutions. Let's do another example. What if we have x1 t to be cosine omega t and x2 to be exponential of I omega naught t, right? And then our Wronskian is cosine omega naught t exponential of I omega naught t. Take a derivative and I get omega naught sine of omega naught t. And here I get, when I take a differentiation, I get I omega naught times exponential again. And the Wronskian is the determinant of this whole quantity. So let's see what that determinant is. So that's I times omega naught times cosine omega naught t times exponential of I omega naught t. And again, you get this plus. I have to take the product here. So that's plus omega naught times sine omega naught t times exponential of I omega naught t. I can take certain things common here. So that's omega naught. Let me take the I also out. And I have I omega naught t. And that gives me a cosine of omega naught t. Since I've taken an I out, I have to put in a minus I in the second term. So it's minus I times sine of omega naught t. Remember from your Argand diagram and complex numbers, cosine omega naught t minus I omega sine of omega naught t is exponential, right? This is exponential of minus I omega naught t. So that gives you, that's equal to I omega naught t times exponential of minus I omega naught t. The two exponentials cancel exactly. What I got is I times omega naught alone, and which is not equal to 0 again, which tells us, which implies that these are independent solutions. Solutions. Okay. So let's stop here. Uh, in the next video, I'll come back and talk about how we can do the same thing for damped harmonic oscillators, and we'll bring in more of physics there. What are the examples for damping cases, and how different solutions behave differently. So let me stop here. So let's stop my recording and see you on the next recording.